Alright, so today we are proving parallel and perpendicular. So there's some theorems that we need to know, and we'll be going over those as we go. Okay, proving parallel we've already gotten very good at. We've got a couple more theorems about proving parallel, and then proving perpendicular we haven't really gotten into. So here's our first theorem. I'm going to change the names of these theorems because theorem 13 seems kind of silly. So it's theorem if two lines are parallel to the same line, they are parallel to each other. I'm going to call this my parallel transversal theorem. Because it's using that transversal theorem, but with parallel lines. So it's saying that if A is parallel to B, and B is parallel to C, then we can say that A is parallel to C. Which makes sense to us. We're like, well, duh, if they're all parallel to each other, then yes. Does that make sense? Okay. So, let's go over another one. So that's my parallel transversal theorem. This is my, I don't know it yet. We'll name it in a second. In a plane, if two lines are perpendicular to the same line, they are parallel to each other. I usually call this my if perpendicular then parallel, just because of what we're dealing with. So this is saying that if M is perpendicular to T and N is perpendicular to T, notice that they are on the same transversal, then you can say, this is actually by corresponding angles that they're parallel, by the way. Then you can say that M is parallel to N. So this is also considered corresponding angles, but this is very specific because you guys know what the word perpendicular is. Okay? So, this is if perpendicular to the same line, then the two lines are parallel. This one's very similar, but the other way. So this is like the converse to corresponding angles. This says if N is perpendicular to L, so we know that angle, and L and M are parallel, then we can also say that N is perpendicular to M. So this one is my, you guessed it, if parallel then perpendicular. Because this is the converse corresponding angles. That's where it's coming from. That's where it's being derived. It's just a very specific case in which there's perpendicularness going on, which is kind of fun. You would use this a lot if you were ever going into construction because you want to make sure it's easier to check if something has a 90-degree angle and it's consistently 90 degrees than to see if two lines are parallel. Just saying. So this would be a very useful theorem to know. Alright. So, I want you guys to try this one. It gives you a bunch of information, and then it wants you to say what has to be true about angle 1, 2, and angle 3. And then if they place D, what is it to the other pieces? Okay? I want you to think about that. This is a lot of structure. So like 1, 2, and 3, those are all on empty space. And then the stuff in pink is the lattice structure. Okay? And then I want you to look at this one. You're creating like the same thing. You're doing a proof. So in a plane, you've got a bunch of information about it. You're going to prove that A and B are parallel. A and D are parallel using that information and using those theorems that we just talked about. Okay? And then I want you to determine the measure of each angle and find the angle, find the value of x. I promise you are able to find all of this information just based on a couple of things. The first one being that these lines are parallel. So you're able to make a lot of inferences about that. And you're able to see that angle 4 is a right angle. Okay, so you already know what angle 4 is, and you are able to find all the other information about this based on that. Okay? And once you're done with those two proofs, You are done for today. Notice that PC 21 is next time, so please study up.